Hello, everyone. Do a sound check. Can you folks hear me?
Yeah, we can hear you.
Anyone please answer that? Can y'all hear me?
Yeah.
Yeah, we can hear you.
Okay. Can you type whether you hear me? Because it seems like I may not be able to hear you, in which case I got to get my headphones out again. If that works, hopefully. Okay. I'm not muted, but I will check my volume, make sure it's up high enough. So I'm not on mute. How about now? Can I hear you guys?
Testing.
Yes, I hear you now. Excellent. I hate wearing those headphones. I don't mind the speaking quality. It sounds pretty good actually on the other side, but it's just a pain to wear them. So I was trying to look through my notes and I realized evidently I forgot to post your the notes from Wednesday, so I don't remember what we did last. That's not a good scenario. I know Monday I had to scrap it about 15 minutes into class, so I figure I'm somewhat behind, and I'd asked you guys actually to watch the N05B class for that one. So that's hopefully y'all did that already. That would bring me to conclude that I started off at that, basically the same thing that N05B finished off with on Monday, and then Wednesday I probably would have started with what they finished off with and started into, for instance, talking about lepton numbers, baryon numbers, and stuff like that. So is that accurate? But we last just covered or talked about baryon numbers and lepton numbers, but I probably only showed one reaction as to whether it worked or not. Anybody recall from their notes last night?
Yeah, you just finished one.
Yeah, just finished one example, and that was
you
one
just
where
finished one and went slightly over. So
Gotcha.
You said stick around for a little bit.
Gotcha. Okay, so yeah, what we'd gotten up to basically, if I'm reading what he's saying right, was we had gotten to the idea that there became a buttload of particles, and the particles, at least the fundamental ones, turned out to be just the gauge bosons, which seem to have no structure and are made of nothing. The leptons, which seem to have no structure and be made of nothing. In other words, not made of smaller particles. And then I said the leptons and gauge bosons, right? Yeah, leptons and gauge bosons, and then the quarks. And the quarks make up the hadrons, and the hadrons can be broken up into two categories: baryons, which is sort of the expansion of what was called nucleons, because it includes the proton and the neutron. But the baryons are made up of three quarks. Okay, whereas the mesons, which is the other part of the hadrons, the mesons are made of a quark anti-quark pair. So that's the rule of what all the things we have are. So I think I'll go ahead and start off with writing that down, and then realize that when we started finding all these particles, as Yukawa had taught us, there was these particles that were exchanged. In lieu of thinking of forces, we think of them fighting over a particle, and in the case of attractive forces, and in the case of repulsive forces, they were firing, their gauge particle from themselves, which would cause them to recoil, and then the other one would catch it, and that call it the recoil, and that's what would make them separate. So that's the fundamental idea. I think I also did I tell you about toes and guts and string theory and quantum loop gravity? Did I mention that to y'all at all? I mean, I didn't teach anything about it other than what it was. Do y'all recall whether I did that or not? Will Dawson said, yep, but I think that was when he was talking about hearing me. Yeah, that was earlier.
I don't remember hearing anything about it. You might have, and it might have just slipped past my mind since you never thoroughly taught it.
No problem. I'm going to go ahead and turn on my, it's my fault anyways, but I appreciate you as much help as you're giving me. So let me go ahead and turn on my document cam. I'm going to sort of recapture what I just said. So the landscape of elementary particles right now, and today is 12/3/21, and this is PHY 241 D01B. Okay, so the landscape is there's certain elementary / fundamental particles. Okay, they seem infinitesimal. In other words, we actually believe they're infinitesimal, and we continue to try to measure their size, but so far their sizes have been maybe smaller than 10 to the negative 18th meters. Okay, so remember the nucleus is about 10 to the negative 14, 10 to the negative 15 meters. This guy is 10 to the negative 18 meters. That's the we've been able to guarantee that it's at least smaller than that for these particles, and they do not appear to be made of anything else. Okay, they include quarks, and for the record, we have initially all we had was the up, down, and strange quark. So we had up, down, strange, but eventually we found 3 more, and that was charmed, bottom, and top. So those are the quarks. We have the gauge bosons. And I mentioned, hopefully I mentioned it to you. If not, I'm going to go ahead and mention it again anyways, even if I did. But the gauge bosons are given that name because gauge theory is the closest thing approaching it, and is somewhat of a gauge theory, is when you were working conservation of momentum or conservation of energy problems, and you had like a roller coaster. And maybe you knew that this was 10 meters high, and this was 30 meters, and this was 75 meters. You could have said the potential energy is 0 here, in which case the potential energy here would be m times g times 20, and the potential energy here would be m times g times 65, right? Or you could have said u equals 0 here, okay? And basically all that would do is that would add an extra plus to the potential energy. So your potential energy here would be mg times 10, mg times 30, and mg times 25, 75. So you see that you added an extra mg 10 to everything. Well, because we only care about differences in potential energy, because the difference in the potential energy results in a difference of kinetic energy. So maybe we knew, for instance, the velocity here, and from that we can find the velocity here, because all that really mattered was the change in potential energy. This adding of mg times 10 didn't matter at all, right? And we either use the difference when we're doing conservation of energy problems, or if we wish to take the try to find the force from the potential energy, remember that's F equals negative gradient of u. That's the way you find the force. That's a derivative. So when you take the derivative of it, since you added a constant, that's still going to not matter. So that's what a gauge does. A gauge theory does. It finds the ways you can alter something such that the things you measure don't really change. but other things do. And by doing so, you can get answers. And that's what these gauge theories were. And they came up with bosons that they could add that didn't cause problems. And then lo and behold, they one by one found them. Okay, so that's why they're called gauge bosons. But they are, for instance, for the strong force, which is the strongest, strength of this, of course, I think I already gave you this table, but it doesn't hurt to see it again. And the gauge bosons are, in this case, the gluons. So that's an elementary particle. The electromagnetic force that's about 10 to the -2. In other words, 1/100th the strength of the strong force. And that one is the photon, which is also listed as a gamma, okay, like gamma radiation. Then the next one is the weak force. And the weak force is about 10 to the -6 times as strong as the strong force. So it's 1/1,000,000th the strength of the strong force. And that is the W and the Z particles are their gauge bosons. And then finally, we have gravity. That's the 4 forces of nature, which used to be 5. Electric and magnetic were 2 separate initially, so they were 5. And this one, if the particle actually exists, has been called the graviton, but we have not found it. Okay, so those are elementary particles as well. And then we have the leptons. And the leptons are, well, the electron's the model one, but the other ones are like the model one, except for the fact that the model one comes along with a neutrino. Okay, and then those neutrinos are like the other neutrinos. So here's the deal with this: we have the electron, and the electron neutrino. That Enrico Fermi named. So this is called E minus, and this is called nu sub E. So that's the Greek letter nu there. It looks sort of like a V. Some books use that as a symbol for frequency in different chapters. So you might see it like that as well, but that's that number. Then we have the muon, which is mu minus. And by the way, the mass of the muon is on the order of 207 times the mass of the electron. Okay. And then with that muon, we have the muon neutrino. I think I'm supposed to spell that. I think it's supposed to be EU. Sorry, I'm laughing at myself. The muon neutrino, which is this. Okay. And then we have the tau particle, which actually I just write out as TAU. And its symbol is tau with a minus sign. This is another particle, just like this is another particle. And then we have the tau neutrino. Oh. Yeah, this, I don't know why I wrote newt here. I laugh at myself when I make stupid mistakes. The tau neutrino is given the symbol this with the tau, and they don't actually put the negatives down there, but I like to sometimes write them just to remind you that all of these particles are like electrons, so they're all positive, I mean negatively charged. This one's mass, by the way, is about 3,000 times the mass of the electron. So the muon and the tau particle do behave like they're major electrons basically, but they're much more heavy, except for the electron. And then of course they have the antiparticles, which is the positron. Whoa. which is E plus, and the anti-electron neutrino. Then they have the antiparticle, of course, of the muon, so that'd be the anti-muon, which is, excuse me, I wrote tau already. The anti-muon, which is mu plus, and of course that comes with a neutrino as well. That's the antineutrino. So that's the antineutrino of the mu neutrino. And then finally we have the tau, anti-tau particle, which is tau plus. You could also write it as tau with a bar over it. So I could write tau bar. I could write mu bar, and I could write E bar. Those are all acceptable. But with that, of course, comes the tau neutrino, antineutrino, that is. Okay. So you can see we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 leptons. Those are all the elementary particles. All the other stuff is hadrons. And hadrons are made up of mesons, which are 1 quark plus 1 antiquark, and then baryons, which is 3 quarks slash antiquarks. In other words, it's got to be 3. It could be, you know, an antiquark and 2 quarks, or it could be 2 antiquarks and a quark. It doesn't really matter. The main thing is that's what makes them up. So these are made up of quarks, which come up here. Of course, the electrons are elementary particles on their own, but they also live on their own. The quarks don't live on their own. If they are out free, they get scooped up really instantaneously almost. And then finally, you got the strong force the bosons, and they're also like the quarks in that they don't appear for very long. Okay, so that's the display of the current state of electricity, or excuse me, of elementary particles. The baryons, by the way, do include the protons, neutrons. But if you look on, no, it isn't. Okay. If you look on the table, you can see baryons also include the lambda particle, and of course its antiparticle. Everything has an antiparticle. We also have the sigma plus plus, and they subscript that C, and I don't know why they subscript the C, but I'm just going to write it down because that's what your other one's saying. Plus you have the sigma plus C, and plus you have the sigma 0 with a C, and then you have the gamma particle that's not charged, B. So remember, when you go from particle to antiparticle, the charge changes, the mass doesn't, but the charge changes, and usually the other conservation numbers do, like the lepton number, the tau number, the electron lepton number, the muon lepton number, and the tau lepton number. They change when you go from the particle to the antiparticle. Same thing with the neutrinos. So all these have their lepton numbers being +1. All these have their lepton numbers being -1, and everything else has no lepton number. All of these baryons, and this isn't all of them, there's a ton more. You can look on a bigger table. I was looking at table 43.4. But if you look at the other bigger table, which that one was on 1183, this one's on 1179. The bigger table shows that the baryons also include the Z particle, which is actually written like this. It's one of the harder uppercase Greek letters to draw. and the omega minus particle, which I talked to you about before. I handed that you. Remember that diagram I told you that I said it looks almost right, but it's missing the dot. So they predicted the dot existed to make the picture pretty. And lo and behold, they predicted the existence of the omega minus particle. That's it. So that's a more complete list of those. The mesons, on the other hand, they include the pion, the kaon, the etaon, and the rho. The pion, the kaon, the eta particle. I should make this capital like that. The eta particle and the rho. So the pion obviously is written with the symbols pi, but it's a plus naturally. And then there's a plus, a 0 one. The antiparticle of this is the pi negative. So, and then this is its own antiparticle. That's called a Majorana particle. The kaon, of course, is just a K plus. But there's also a K0, and the antiparticle of the K plus is the K minus. And then they have a K0 strange and a K0L, all sorts of weird stuff. The eta particle looks like this, and its natural state is actually the 0, and it's its own natural antiparticle. And then the rho particle, rho 0, has an antiparticle that's itself another Majorana particle. And then they also have the rho plus, which has an antiparticle of rho minus. So that's a little bit more complete list, just to give you examples of everything. So everybody see what the elementary particles are. As you said, this is the kind of list you should be able to make, maybe not with more than proton and neutron for the baryon, and maybe the pion for the meson. If you can give me one example of a meson, I'd be plenty happy with that. So really, that's what you're shooting for, is to know that there are in fact 6 quarks. I don't even require you to remember the 6 names, but I would hope you would be able to see if I said up or slant. Which one's a quark? You probably say, oh yeah, up quark. So just look over those names and know them, but don't plan on having to recite them or anything like that. But I wouldn't be surprised if you saw a question like which one of these is the actual quark, and do something like up versus left, or down versus right, or something weird like that. Okay. The gauge bosons, I do expect you to know those. The gluon, the photon, the W and the Z particle, and the graviton. And I do expect you to know the leptons. Okay. So those are just the sort of thing. And then you should know that the rest of the particles that are actually made up of those elementary particles, are the hadrons, which are broken up further into the mesons and the baryons. And I do expect you to know, of course, that mesons are 1 quark and 1 antiquark, and that the baryons are 3 quarks / antiquarks. Okay. So these are all important things to know. Like I said, if I did ask you an example, I would expect you to remember pi, proton, and neutron, and that's probably plenty enough for examples of hadrons. Okay, because then you've got the pion, which is the one case that you've seen in several problems we've worked throughout the semester of a meson. Okay, now about this part. Okay, this is where the Holy Grail, or a Holy Grail of physics, comes in. So one of the ideas that is going around in physics that we really would like to address is when we originally had 5 forces, as I told you about, and actually, to be honest with you, they didn't necessarily know the existence of the strong force or the weak force when the electromagnetic force was made into one. But the works of Maxwell and Faraday and Gauss and Volta and all those people putting together, that ultimately culminated with Maxwell's equation, that put the final nail in the coffin and said, hey, the electric force is another way of seeing the magnetic force, and the magnetic force is another way of seeing the electric force. You can literally use relativity and consider a frame where you're standing next to a wire carrying a current and you're sitting still. Okay, that current carrying wire creates a magnetic field acting on you, right? And in fact, if the current's going downward, then the magnetic field is going around it like that. Okay, so at the bottom, it's pointing that way. To the left of the wire, it's pointing up. To the top of the wire, it's pointing this way. And to the left of the wire, it's pointing that way. That's an actual magnetic field that's created due to a current carrying wire carrying a current downward. Now, if you jump to the reference frame in which the positive particles that are supposedly moving this way are no longer moving, then you have no current, right? So you can't have a magnetic field because you don't have any charges moving, and the force on a particle due to magnetism is F is equal to QV cross B. So you can see if you don't have a Q, in other words, it's neutral, or you don't have a velocity, you can't have a magnetic field, and therefore you can't have a magnetic field force. So still both frames, according to relativity, have to agree that there is a force over here to the right of the particle that's pushing the object upward. Okay, in other words, that's the direction of the magnetic field, and that's where the direction of the magnetic field should apply. That if you had a positive particle, for instance, moving, let's say this way, then QV cross B would actually create a force going into the page. Okay. Now you still have to make the same conclusion, even though you're in a frame now where there's no current. Well, if you use the relativistic frame, which actually you don't even have to, because Maxwell's equations are already set up for relativity. In other words, they're already relativistically correct. Now, if you jump to that other frame, you actually calculate that there's a dispersion of charge, because the charges that were moving this way also had negative charges moving this way, and the gaps between them due to length contraction forces there to outnumber the number of particles going in the positive direction. So you get a net charge on what had no net charge, and therefore you create an electric force that is exactly the same magnitude, direction, and everything as the magnetic force had been in the other frame. So that's what one of the major things that Maxwell's equations accomplished was it showed us that the electric field and the magnetic field are just two versions of the same thing. So that was a unification of the 5 forces into 4. But like I said, at that time, they really only knew electric, magnetic, and gravitational. Later on, we did have, of course, 4, which had been the strong force, the electromagnetic force, the weak force, and the gravity force. And 3 people, Sheldon Glashow, I've met him a couple of times. He was really nice to me. One of his good friends who actually ended up spending quite a bit of time in Brazilian prison was wanting me to be his graduate student, and I was his quantum mechanics student at the time, and he introduced me to Sheldon Glashow as his best quantum mechanics student. I failed the exam shortly thereafter. It felt really bad, but anyways, he introduced me. So Sheldon Glashow was really super nice to me, and the subsequent times I met him, I spoke with him. He was nice as well, but he's really rude to a lot of our faculty, so I don't think he's a very, very nice person. And specifically, he was very rude to our female faculty. Just dismissed their questions like they were idiots, and it was really bothersome. But anyways, him, who actually was a fellow student in middle school and high school with a guy by the name of Steven Weinberg. And I should have looked this up by now, but I think it's Abdul Salam. I think his first name was Abdul, but I could be wrong. His last name is definitely Salam. These 3 guys independently came up with what's called the standard model. Okay, so imagine having these 2 guys in your class. Wouldn't they wreck the curve? Both of them, went to middle school and high school together in New York City. They all simultaneously came up with the same idea, the standard model, and they all shared the Nobel Prize for it. Steven Weinberg just passed away. I think Abdul Salam and Sheldon Glashow. I know Sheldon Glashow still alive, but I literally just talked to Weinberg maybe 6 months ago. I just, here, I'm a nobody. I sent him an email, at his University of Texas site and website, or his University of Texas email address. And he replied to me the same day, and we had a 3 or 4 day conversation. Just a wonderful human being, nice to everybody, brilliant guy. So I really like Steven Weinberg. I haven't met Salam, but either way, these 3 guys won the Nobel Prize for creating the Standard Model, which went on and actually did something major. So the Standard Model basically saw or managed to unify the strong force and the electromagnetic force, and then over some time they were able to pull in the weak force. I might be missing the order. Maybe they did the EM force first and with the weak force and then did the strong force, or maybe they did the strong and the EM and then did the weak force. I can't remember. But the main thing is they unified all these. They now have a picture in the Standard Model that shows these 3 forces being, different sides of the same coin, just like electricity and magnetism became different sides of the same coin. So that's a big deal. And that's one of the holy grails of physics, is to take these and include gravity in that. And such theories are called guts, grand unified theories, and toes, theories of everything. And a couple of examples of them are string theory, and I'm going to write the theory in quotation marks. Oh, I almost said stringy theory. String theory. Okay. Now, theory in modern use is supposed to mean a very strong word, meaning something that has made numerous hypotheses that have been verified, shown to be true, and has never once had one done properly shown to be wrong, and has gone through process hundreds of thousands of times. That is not what string theory is in the strict sense. Another one is quantum loop gravity. And if you watch Big Bang Theory, you'll know that that's one of the debates that Leonard has with his girlfriend, who oddly enough was his girlfriend also in the Roseanne Barr show. But now I think she's a violinist and he's a cellist, and they play music together, but then they sort of start dating for a while, and they're dating and they're getting really serious. And then all of a sudden, Sheldon points out that she's into quantum loop gravity, and Leonard believes in string theory. He said, well, what will we raise our kids on? And Sheldon's Leonard says, I think I'll let them decide. Oh, you monster, you can't do that. But it's kind of funny. But those are the 2 most active attempts to unify these things. They were mathematically constructed. Partly, this one was mathematically constructed by Ed Witten, who's now the Lucasian professor of mathematics at Cambridge. In other words, he took the spot that Stephen Hawking had, and of course Maxwell had before him, and of course Dirac had after Maxwell, but Newton had before Maxwell. So that's an esteemed position. Ed Witten created this, and in fact there was like 9 different versions at one point, and Ed Witten and some other people showed that they were all equivalent. So these are the 2 bigger games, but the problem is both of them, they predict a lot of stuff we already know, which makes you feel good if you come up with a theory that can predict, for instance, why the gravitational constant is 6.63 times 10 to the negative 11th. That's a really, really good thing, right? But it might be that by understanding the symmetries and things that you forced into this theory, that you created a system that required all the things we already knew to be true. We just didn't understand the inner workings. So it predicts all these things that we already knew to be true. And in some sense, if we had invented that, say in the time of Newton, then we would have even beat Newton to gravity and all that stuff. We would know all that stuff that Newton found. We'd know all that stuff that Maxwell found, period. But we didn't do it that way. So we really don't get credit for predicting something that already existed. Now, it also makes many predictions that can be tested. But the problem is the predictions, at least the last time I checked, and this is not my area of expertise, so I haven't checked actual publications on this in well over a year. But the thing with string theory and quantum loop gravity is basically they make a lot of predictions that we could in principle test, but we're probably not going to be able to test for 50, 100, 200 years. In that sense, these 2 may not even be what we call a scientific hypothesis. You can argue that it's not a scientific hypothesis because you can't falsify it right now, right? It it says the things we already knew. It didn't give us that, but it said it. The same thing with quantum loop gravity, and all the things it does say that we don't know, we can't test. So it's almost like it's not even a hypothesis. So that's where there's a fight. A lot of people don't like us doing research in string theory and quantum loop gravity. A lot of them are just sort of doing a quantum gravity hybrid. So where you're trying to make quantum mechanics mesh with gravity on a case-by-case basis. But that's really all we got going on. And if we found that, of course, if someone can do this, can pull off one of these ideas that shows all of these being the same thing, they will absolutely win a Nobel Prize. I mean, I'm almost certain of that. But it's really, really difficult. Gravity is a beast to try to fit in with quantum mechanics. Even the little bit I know is very, very difficult to even think about. So, and the universe doesn't know what's a damn thing, right? There's no reason these things had to be one and the same, and there's certainly no reason that all four have to be one and the same, because the universe doesn't know us anything. We're just really fortunate that the universe gave us laws of nature that we were able to put down in mathematical form as we do in physics. So that's what the Big Bang theory, or excuse me, that's what the string theory and quantum loop gravity and quantum gravity hybrid things come up with. Wald has worked some of those out. Wald's a famous author and a professor at University of Chicago, which you probably remember. That's where Obama went. That is really a great esteemed university. University of Chicago is where Fermi was. That's where the first nuclear reactor was built. Fermi's the first person to have made that reactor there. That's where Fermilab is. It really is brilliant. To give you some idea, the textbooks that I used as a graduate student for mechanics and as a graduate student at East Carolina for quantum mechanics, they were used for undergraduates. And then their grad students would use books that are just the Springer Verlag books, and they're literally like a nightmare. You have to be a PhD mathematician to more or less read them. So it's really an impressive institute. So you always watch for places like MIT, Stanford, UC Berkeley, and of course on the other side, like I said, the MIT is in Boston, but the other stuff is West Coast stuff, and then Chicago's Midwest. But those big universities, Princeton, Harvard, Yale, those places really put out excellent stuff. Not all the time. I mean, a lot of people come from other places. Sheldon Glashow didn't go to, actually, I don't think he went to MIT. So anyway, so that's where we are. Any questions on all that hodgepodge? It's a big nightmare, right? So another thing to remember about the leptons is the leptons do not partake of the strong force. In other words, they're not affected by the strong force. Leptons do not participate or partake of the strong force. So I just mean they never interact via a strong force. And it turns out that these forces basically require decays that are super rapid if the force is strong. So for instance, for the strong force, the decay time is on the order of 10 to the negative 24th seconds. The electromagnetic force is on the order of 10 to the negative 13, or excuse me, 10 to the negative 16 seconds roughly. The weak force is on the order of 10 to the negative 13 or larger. Okay. And gravity, we don't even talk about that, but that gives you some idea. And therefore, if you're asked to solve some physics problem to say, hey, does this reaction occur? And they give you the hint that it happens, 10 to the negative 22, 10 to the negative 24 seconds or something like that, then you automatically know lepton number does not have to be conserved. Okay. So this time period suggests lepton number is not conserved. So it's kind of weird. We have these conservation laws like the baryon number I mentioned to you guys. The baryon number is, guess what? +1 for all the baryons, -1 for all the antibaryons, and then 0 for everything else. That conservation of baryon number is as valid as conservation of charge, conservation of momentum, conservation of energy, conservation of angular momentum, all the things we've learned so far, all of the conservation of mass energy, all of those are on the same footing with baryon number. So baryon number absolutely must be conserved. You know, of course, also that technically linear momentum is not conserved unless the net force on the system is 0. Same thing with linear or angular momentum. It's not conserved unless the net torque is 0. But that's the only conditions. In the case of lepton number conservation, that's only conserved in reactions that involve the weak force, the electromagnetic force, and of course gravity is irrelevant, but gravity does act on the leptons. Okay. So those are some rules to keep in mind. Now let's do a couple more examples. We only got about 6 minutes, but I've pretty much covered the entirety of the chapter. It's just now a matter of you doing examples like the examples in your book. Let's do, for instance, the sigma plus into the, no, I think I did that one already. Yeah, I got the negative mass. Yeah, I did that one for you guys already. Here's a neat one, pi minus plus p. So pi minus plus p, the proton, yields K0 plus the lambda 0. Okay, so you might want to know, does this work? Well, it turns out that in the early 1950s, these new particles, the K-ion, the lambda particle, the sigma particle, were found to behave rather strangely in 2 ways. First, they were always produced in pairs. So you see that if a reaction like this would occur and you got a K-ion, a lambda particle, or a sigma particle, they would come in a pair, like you'd have 2 sigmas, 2 Ks, or a lambda and a K, or something like that. So that was strange and occurred with a high probability, but a similar reaction where you had, say, pi minus plus a, let's say a proton again. This did not occur, and that was where you had a K0 and say a neutron. That's what they meant by coming in pairs. This reaction is not going to happen because it didn't come in a pair. So because of that, they introduced a number, strangeness. Okay, and it's S. And basically the way the strangeness works is that strangeness is a 1 for the strange particles, and it's a 0 for everything else except for the anti-strange particles, in which case it's a -1. And it turns out, to explain the decay of strange particles, assume that the strangeness is conserved in strong interactions, but is not conserved in weak interactions. So here's another rule for you. Strangeness is conserved in strong interactions. Again, strong force, meaning decays that take 10 to the -24 seconds or around that time. In strong interactions, but not in weak interactions. And these are on the order of 10 to the -13 seconds. So there's some other rules that we got to keep in mind. So the lepton number isn't conserved in strong interactions, but the strangeness number isn't conserved in weak interactions. And again, we either have to tell you that, or we give you something like the time period that it takes and that sort of stuff. The weirdness, though, there is one other thing that's weird. When we looked at this and we said the weak force the weak force broke down in like 10 to the negative 13 seconds for the W and the Z particle. Well, it turns out actually no, even though that's about the weak force, these are on the order of 10 to the negative 20, I think 22 or 24 seconds. So the weak force is always a long period of time, like 10 to the negative 13 seconds, except when the decay is producing the W and the Z particle, in which case they're more like a strong force thing. Okay, so those are sort of the scary little rules that you have to keep in mind when you go to check something. So if you look at this, you'd say the strangeness on this side is, of course, 0. And then the strangeness on this side is, of course, 1 plus negative 1. Which also equal, or excuse me, I'm writing it under the wrong thing. I was writing it for the one to the left and just blindly started writing it over here. So the strangeness on this one is 0 plus 0, which equals 0. The strangeness on this one is positive 1 plus negative 1, which also equals 0. So that one works. However, on this one, you get 0 plus 0 equals 0. On this one, you get the plus 1 plus 0. So it does not work there. Okay. So that was able to explain that. That's really the crux of the rest of these problems is let's check things like, tell me if I did, is this the one I did with you last time? I don't think it was. I think the one I did with you last time was dealing with Qs, but the pi minus plus the proton yields the K0 plus question mark. No, I didn't work that one with you at all. I know for a fact. Okay, so let's look at baryon number. Well, first off, let's look at charge. I always try to look at charge first because that's the easiest. This is plus 1 plus, or excuse me, that's minus 1. What am I thinking? This is minus 1 plus positive 1, which equals 0. This one is 0 plus question mark. So that implies the baryon number for question mark must equal 1. Okay. Now we check, I said baryon number, the charge number, sorry. Now the baryon number is what we check. And of course, the baryon number for this reaction is 0 for the pion. Remember, the pion is one of the mesons. It's the only meson I told you should know. Of course, the proton is an actual regular particle, not an antiparticle, so it's plus 1. So we get 1 for this result. Over here, we get the kaon, which has obviously the K particle is not even a baryon, so it actually has a baryon number of 0 plus question mark. So this clearly says the baryon number of question mark must be equal to 1. Okay. Now we can check the lepton number, and we'll check. There isn't a lepton for any of these. So we'll say 0 plus 0. Remember, they're the electron, the mu, and the tau. They're not in the left-hand side at all. So this has got to equal 0. And then this is 0 plus question mark. So this means the lepton number L sub E equals the lepton number L sub mu equals the lepton number L sub tau must be 0. Okay, so it can't be a lepton or an anti-lepton. Then we have the strangeness number. And this one you actually have to look up. Of course, I told you how they are. The strange particles, the K, the lambda, and the sigma, they have a strangeness of 1, and their antiparticles have a strangeness of -1. So in this case, these are not strangeness at all. So that's 0 plus 0. And then this kaon is a strange particle. And in fact, we learned that its strangeness number is +1 plus that. So we know that the lepton number, or excuse me, the strangeness number must be equal to, since this side was 0, this must be equal to -1. Okay. Now we just did a previous result where we had the pi plus the proton gave us a K and a sigma, a K and a lambda. So we know the lambda works. We're actually looking for something other than that. So if I look on the table and look in baryons, because the baryon number has to be 1, and then we only look at the positive charge things. So I see the lambda plus is in there, but the charmness we didn't talk about at all on this one. We didn't have to. The strangeness, though, being a -1 leads to only the strangeness is -1, right? Yeah, strangeness is
Shouldn't your charge be 0?
One. Oh, thank you. Yeah, that's good. That was what was screwing me up. Yeah, 1 plus -1, or excuse me, this is -1 plus +1. That's 0. So that, yeah, this side had to be 0. Thank you. That was what was screwing me up. I was like, I'm not seeing the particle. But now I look on that table on page 43, or page 1183, 43-4 is the table. And when I look on that, actually, I see the only one that works is the sigma 0. That has a baryon number of +1. That has a strangeness number of, no, that's not it. Oh, let me check the other table. This table is not giving me one that I want. So I'm going to check the other table, which is on the page 1179. I'm still looking for a baryon number of 1. So I got all that proton, neutron, lambda. Yeah, okay, that works better. I have to have a charge of, you said 0. So if I look at the ones with charges of 0s, then that gives me the lambda 0, that gives me the sigma 0, and that gives me the xi 0. But the xi 0 has a strangeness number of -1, but the sigma 0 has, or excuse me, a -2, but the sigma 0 actually has a baryon number of 1 and a strangeness number of -1. So the answer is the sigma 0 particle. That's it. And we actually ran out of time anyways. So of course, everybody's free to go. So that's a typical example where they have a blank and you have to use these rules to figure things out, but you've got to keep those other wordy rules. Remember, these are the things that you can't get from just looking at the equations. You actually got to read the text. And sometimes the author's kind enough to put the text in italics or bold print to make sure you get it. But other times he didn't. Like, he didn't put any of these time periods that I put for these reactions or these decays. He didn't put any of that stuff in parentheses or in italics or anything. So you got to fish those out yourself. That's why I gave them to you here. But that should finish chapter 43 on Monday. When you come back, we will start with chapter 44 and we'll be done. Remember, the rest, I'm not sure about next week's labs, but the rest of the classes will be spent on 44 and just preparing for the final, which is for you guys would be Wednesday of not next week, but the one after. Thanks for coming, everybody.
Hey, Professor, I have a quick question.
Yes.
So I was going through the old tests and I started making an old study guide for myself for the final.
Right.
And I noticed that for the test, chapter 11 and 36, those questions are actually hidden from us. The other ones are available.
What test
for
was
us
that?
Chapter 11 _ 36. So I think it's chapter 11 and 36.
Okay, I'll make those available too. Thanks for letting me know that. That would stink.
Awesome. Thank you so much.
No problem. Remember, lab today is just a review session. Those of you who have lab today, not required to attend, but if you do attend, I'll be answering any questions. It's student-driven Q&A session. Catherine and Randall, do y'all have any questions? I'll go ahead and split. Yeah, Catherine asked about that. Good.